Welcome to this lecture on one of the most pivotal moments in 20th century physics. Today we'll explore how Niels Bohr solved a profound puzzle that had stumped the greatest minds of his era, the hydrogen emission spectrum. By 1912, physicists faced a crisis. Classical electromagnetic theory predicted that orbiting electrons should radiate energy continuously, producing a smooth rainbow of frequencies. But experiments told a completely different story. Picture an electron orbiting a proton. Classical physics says this accelerating charge must continuously emit electromagnetic radiation. As it radiates, it loses energy and should spiral inward, eventually collapsing into the nucleus in about 100 picoseconds. But atoms are stable. They don't collapse. Something is fundamentally wrong with the classical picture. When physicists passed electric current through hydrogen gas and analyzed the light with a spectrograph, they saw something extraordinary. Not a continuous spectrum, but sharp, discrete lines at specific wavelengths. The Balmer series showed lines at 656 nanometers, 486 nanometers, 434 nanometers, and 410 nanometers. These weren't random, they followed a precise mathematical pattern. In 1885, Johann Balmer discovered an empirical formula that fit these wavelengths perfectly. Later, Johannes Rydberg generalized it. 1 over lambda equals the Rydberg constant times the quantity 1 over n final squared minus 1 over n initial squared. The Rydberg constant is 1.097 times 10 to the 7th inverse meters. This was measured with exquisite precision. For the visible Balmer series, n final is 2, and n initial takes integer values 3, 4, 5, and so on. Here's the critical question. Why should atomic spectra follow this bizarre formula with integer quantum numbers? Classical mechanics offered no explanation whatsoever. Classical electromagnetic theory predicted a continuous spectrum. As the electron spirals inward, its orbital frequency should change continuously, producing every possible frequency in a range. Classical physics predicted something like this, a continuous smear of radiation across all wavelengths. But that's not what experiments showed. Let's examine why classical attempts failed. Several brilliant physicists tried to fix the classical model. Every attempt produced predictions that disagreed with the data. An orbiting electron continuously radiates energy according to Maxwell's equations. The radiated power is proportional to the square of the acceleration. The radiated power equals E squared times acceleration squared divided by 6 pi epsilon 0 c cubed. As the electron loses energy, the orbital radius shrinks continuously. The orbital frequency increases continuously as the radius decreases. The orbital frequency equals 1 over 2 pi times the square root of ke squared over mr cubed. Since the radius changes continuously, the frequency should also change continuously. This produces a continuous spectrum, completely contradicting the observed discrete lines. Some physicists attempted to fit the Rydberg formula using classical mechanical models. They tried various potential energy functions and orbital geometries. Every single classical model produced the wrong spacing between spectral lines. The curves were either too smooth, overlapped incorrectly, or had the wrong dependence on quantum numbers. The experimental data points showed specific spacing. Classical models produced curves that didn't match. The spacing was always wrong. The dependence on quantum numbers was incorrect. In 1913, Niels Bohr made a radical proposal. He abandoned the idea that classical mechanics applies to atomic orbits. Instead, he introduced two revolutionary postulates. Postulate 1. The electron can only occupy certain special orbits where the angular momentum is quantized. The angular momentum L equals n times h bar, where h bar is Planck's constant divided by 2 pi. The quantum number n is a positive integer. This single condition immediately restricts the electron to discrete orbits. Not all radii are allowed, only specific quantized values. Postulate 2. The electron does not radiate energy while in a stationary orbit. Radiation is only emitted when the electron jumps from one orbit to another. The photon energy equals the initial energy minus the final energy, which equals Planck's constant times the photon frequency. This explains why we see discrete spectral lines. Each line corresponds to a transition between two specific energy levels. Let's derive the allowed orbital radii from Bohr's quantization condition. We'll use classical mechanics for the balance of forces, but impose quantum conditions. The centripetal force equals the Coulomb force. M versus squared over r equals ke squared over r squared. The angular momentum m versus r equals nh bar from the quantization condition. Solving for velocity, v equals nh bar over mr. Substituting into the force balance equation and solving for r, we get r sub n equals n squared, h bar squared over mke squared, which equals n squared times the Bohr radius, a0. The Bohr radius is 0.529 angstroms, or 0.529 times 10 to the minus 10 meters. Only discrete radii are allowed. The ground state has n equals 1. The first excited state has radius 4 times larger. The second excited state has radius 9 times larger. Now let's calculate the total energy for each allowed orbit. The total energy is kinetic plus potential. The total energy equals 1/2 m versus squared minus ke squared over r. After substitution and simplification, the energy of level n equals negative 13.6 electron volts divided by n squared. The negative sign indicates the electron is bound to the nucleus. Zero energy corresponds to a free electron infinitely far away. The ground state energy is negative 13.6 electron volts. The first excited state has energy negative 3.4 electron volts. The second excited state has energy negative 1.51 electron volts. Now comes the moment of truth. Can Bohr's model predict the correct wavelengths for the hydrogen emission lines? The energy difference equals 13.6 electron volts times the quantity 1 over n final squared minus 1 over n initial squared. This energy equals h times the photon frequency. Converting to wavelength, 1 over lambda equals delta E over hc, which gives us 1 over lambda equals 13.6 electron volts over hc times the quantum number formula. This is exactly the Rydberg constant. Bohr's model predicts the Rydberg formula from first principles. This was a stunning triumph. Bohr derived the empirical Rydberg formula from fundamental quantum postulates. The agreement was perfect. Let's calculate the wavelength of the first Balmer line, called h alpha, which corresponds to the transition from n equals 3 to n equals 2. 1 over lambda equals the Rydberg constant times 1/4 minus 1/9. 1 over lambda equals 1.097 times 10 to the 7th times 0.1389. This gives lambda equals 656.3 nanometers, in perfect agreement with the experimental value of 656 nanometers. This is the n equals 3 to n equals 2 transition. The electron jumps from the third orbit to the second orbit, emitting a red photon at 656 nanometers. Bohr's model was an incredible success. It explained the stability of atoms, the discrete spectral lines, and the Rydberg formula. Here's a key question. Why did introducing quantization fix everything? The answer is that quantization imposed constraints that classical physics lacked. In classical physics, every radius is allowed. The electron can spiral continuously inward, radiating at every frequency along the way. In Bohr's quantum model, only specific orbits are allowed. The electron cannot exist between these orbits. Transitions occur instantaneously as quantum jumps. This discreteness is the key. Only specific energy differences are possible, producing only specific photon frequencies. Let's calculate the ionization energy of hydrogen. This is the energy needed to remove the electron from the ground state to infinity. The ionization energy equals E infinity minus E1, which equals 0 minus negative 13.6 electron volts, giving 13.6 electron volts. This prediction matched experimental measurements of hydrogen's ionization energy with remarkable precision. Here's a helpful analogy. Classical physics is like a smooth ramp where you can stand at any height. Quantum physics is like a staircase where you can only stand on specific steps. On the staircase, you can only occupy discrete levels. You can't stand between steps. This is like quantum energy levels. On the ramp, you can stand anywhere. This is like classical continuous energies. Despite its success, Bohr's model had serious limitations. It only worked for hydrogen and hydrogen-like ions. It failed for multi-electron atoms. The model completely failed to predict the spectra of helium and heavier elements. Something deeper was needed. Bohr's model gave no information about the intensity or brightness of spectral lines. It only predicted wavelengths. The complete solution came in 1926 with Schrödinger's wave equation and the full development of quantum mechanics. What's the deeper lesson here? Bohr showed that when theory and experiment disagree, we must be willing to abandon our most cherished assumptions. Classical physics seemed absolutely fundamental. It had worked for centuries. Newton's laws were thought to be universal truths. But nature, at atomic scales, simply does not obey classical laws. Electrons do not spiral into nuclei. Energy is quantized. This was revolutionary. Science advances when we respect what experiments tell us, even when it contradicts our intuition and forces us to develop radical new theories. Bohr's work opened the floodgates for quantum mechanics. Within 2 decades, quantum theory revolutionized our understanding of matter, energy, and the universe. Bohr's ideas led directly to de Broglie's matter waves, Heisenberg's uncertainty principle, and Schrödinger's wave equation. Understanding atomic structure became the foundation for all of modern chemistry. Chemical bonds, molecular structure, and reactions all rest on quantum mechanics. Without quantum mechanics, we wouldn't have transistors, semiconductors, lasers, or modern electronics. Quantum computing is the next frontier. Let me summarize this profound episode in the history of physics. Classical electromagnetic theory predicted that atoms should emit continuous spectra as electrons spiral inward. Experiments definitively showed sharp, discrete lines at specific wavelengths following the Rydberg formula. Every attempt to fit this data using classical models failed. The spacing was wrong. The functional form was wrong. Bohr introduced quantized angular momentum. This immediately restricted electrons to discrete orbits with discrete energies. This single quantum assumption explained the stability of atoms, the Rydberg formula, ionization energies, and all observed spectral lines for hydrogen. The introduction of quantization was not just a mathematical trick. It represented a fundamental shift in how we understand nature. At atomic scales, nature is fundamentally discrete. Energy, angular momentum, and other quantities come in indivisible quanta. This discreteness has absolutely no analog in classical physics. It's not a limit or approximation. It's a new fundamental principle. Bohr's breakthrough required intellectual courage to abandon classical intuition and accept what the data demanded. This is how science progresses. We follow the experimental evidence wherever it leads, even if it means overthrowing centuries of accepted theory.